Hello everyone. I am looking for translator, interpreter, مترجم. Is there anyone here? Is there anyone who helps me? Okay. have to start in Persian. Uh, I don't know. Is there anyone who helps me in English, in Farsi? I start in Farsi. No one answer this question. It's too bad. هیچ این پرسش من جواب نداد متاسفانه و این سوال بود باید جواب داده میشد. خب درسمون رسید تا اینجا. حالا میریم سراغ رفع مشکل سوم در روش حذفی گاوس. اون مشکلاتی که داشتیم میریم به سراغ مقیاس بندی کلی Complete Pivoting. در این روش میگیم ماکسیموم قدر مطلق آی جی ها برای تمام آی رو حساب میکنیم. اگه بشه مثلا قدر مطلق آ پی کیو، یعنی درایه‌ای که از نظر قدر مطلق رخ میده، ماکسیموم رخ میده تو سطر پیوم ستون کیوم باشه، این درایه از نظر قدر مطلق ماکسیموم مقدار باشه، میایم عمل R1P و C1Q رو انجام میدیم. در حقیقت سطر اول با سطر پیوم جایگزین میشه و ستون یک اول با ستون کیوم جابجا میشه. حواسمون هست تو دستگاهی هم که جایگذاری میکنیم X1 و XQ جابجا میشه، چون ما ستونا رو که جابجا میکنیم XI هم جابجا میشه. به عنوان نمونه میگیم فرض کنید این دستگاه رو میخوایم حل کنیم. 4 معادله 4 مجهول 4 1-3 x2 مساوی 9. معادله اول، معادله دوم، معادله چهارم. x1 به اضافه 4x2 مساوی -1. قبل از اینکه شروع کنیم به روند حذفی گاو، این ماکسیموم رو از نظر قدر مطلق پیدا میکنیم. یه لحظه ببخشید. Mrs. Faten, can you help me in translate for English to Arabic? I think Faten is female. Excuse me just a moment. I think this is button could help us. Okay, I try to speak English. We are talking about complete pivoting. Uh, in this method, we first of all calculate maximum absolute of aij for all I and j. If it is apq in absolute mode, means the row in P and the column in Q. We used we do R1P. That means substitute the first row and the P row, and also we do C1Q. That means substitute the first column and Q column. Also, we consider the substitute x1 and q xq because we do c1q. We have to substitute x1 and xq. For example, consider this system: four equations and four unknown variables. First of all, we used uh, partial pivoting and complete pivoting. The both we will do. For partial pivoting, we use the first column. We find the maximum in absolute mode, and it will be in the third equation. We substitute the one and the third equations. Excuse me. First of all, a scaling. Excuse me. First of all, we have 4 minus 3, 2, 5 in the first row. So the maximum in absolute mode will be 5. So we divide the first row in 5. 4 divided by 5, x1 minus 3 divided by 5, x2, and finally 9 divided by 5. In the second row or second equation, we have 7, the maximum. So we divided the second row in the 7, and we got 1 divided by 7, 3 divided by 7, 1 minus 2 divided by 7, and 0. In the third row, we have minus 8. So we divided in the maximum absolute. We divided the second row by minus 8. We have x1 minus 1 divided by 8, x2 minus 1 divided by 4, x3, and minus 3 divided by 8, x4, and finally it's equal 3 divided by 8. And the last one, we have maximum minus 9. We divided the the first, the fourth row equation, I mean, by minus 9, we will have minus 1 divided by 9 x1, and finally 1 divided by 9. This is scaling. scaling مقیاس بندی مقیاس قیاس it's Arabic word. So partial pivoting, you have to you have to calculate the maximum between 4 divided by 5, 1 divided by 7, 1 and 1 minus 1 divided by 9. In absolute, it will be 1. So we change the first row and the third row. I want you to do that, but let me to write that. It will be x1 minus 1 divided by 8, x2 minus 1 divided by 4, x3 minus 3 divided by 8, x4 equal 3 divided by 8. It's the third row. Second row, it's the same. 1 divided by 7 x1 plus 3 divided by 7 x2 plus x3 minus 2 divided by 7 x4 equals 0. And the third row will be the first one. 4 divided by 5 x1 minus 3 divided by 5 x2 plus 2 divided by 5 x3 plus x4 equal 9 divided by 7 divided by 5, excuse me. And the last one is the last equation. Now we use this coefficient, I mean 1, in the first row and change um, this one 1 divided by 7, this one 4 divided by 5, and minus 1 divided by 9, change them to 0. And again, continue. I put that to for you to do uh, for partial by waiting. Now we want to we wrote that here. Uh, maximum between oh this is without any partial, excuse me. It's doing partial pivoting scaling, but here I do partial pivoting without scaling. So I calculate maximum between 4, 1 minus 8 and 1. It will be 8. So we commute first and the third rows. That means R1, 3. So minus 8, x1 plus x2 plus 2x3 plus 3x4 equal minus 3. The second row is the same. The third row is the first one in the previous, and the last one is the same. I want you to do that again and continue. It's no problem. And with complete pivoting, we have this system. We calculate maximum between 4 minus 3, 2, 5, 1, 3, 7, minus 2, minus 8, 1, 2, 3, 1, 4, minus 9, and 6. I mean all coefficients. That is 9 is the maximum coefficient in our system. So it must be go to the first and the first row and the first column. We it is A43 in the row, fourth row and third column. So we do R14, that means substitute the first and the fourth rows, and also C13, that means substitute between the first and the third column. Also we substitute x1 and x3. So we have minus 9 x1. I wrote that in capital mode, plus 4 x2 plus x3. It's capital because it is x1 in little mode, plus 6x4 equal minus 1. The second, we want to write the second equation is the second equation. X1, change that to the x3 in the first column to the third column. So we have 7x1, it's capital mode, plus 3x2 plus x3 in the capital mode, that is x1. And finally, minus 2x4 equals 0. We want to write the third row, that will be the first row in the previous. This is x1. We have 2x1 in the capital mode, minus 3x2. Um, sorry. It's it's the third row. I have a mistake. Third one is the third one. 2x3 change to 2x1, capital X1, plus x2 minus x1 change to minus x3 in capital mode, and 3x4 equal minus 3. And now we want to write the fourth row. That is the second. That is the first row in the previous. We have 2x1 minus 3x2 plus 4x3 in capital mode, and plus 5x4 equal 9. So we after that we have the maximum entry in the first row in the first place. It's the maximum in all of coefficient. We know x1 in capital mode is x3. Previous x3, x3 in capital mode is x1. So we can continue. Its pivot -9 will be in the down, 7 in the up, 2 in the up, 2 in the up, and change these coefficients to 0. I want you continue that. So let me to explain all of them again. We have an example. First one with scaling, we have this system. We can continue in any mode. I mean partial pivoting or complete pivoting. Without any scaling, we can do partial pivoting. We saw in the new, for example, scaling is not necessary to do and to get a good result. So we can drop that and didn't consider it. With partial pivoting, we have to, in the origin system, we have to find the maximum in the first column and then change uh, the first row and the third row. With complete pivoting, we have to find the maximum. It's -9 in row 4 and third column. We want to change that in the first row in the first column. So we do R14, C13. Also, we change X1 and X3. So if we write X1 in the capital mode is X3 in the previous mode, and X3 in capital mode is X1 in previous mode. So we change the system in this chapter, this mode, and we know we can calculate X1, capital X1, 2, capital X3, X4, and finally change X1 and X3. I want you continue and write that. Do that, and if you have some uh, problem, ask me in the WhatsApp group or private WhatsApp. Ask it to me. Example, using complete pivoting in the first example. We have an example. It was a very special example, so we named that the one. Example 1. Because it's very special. We want to do complete pivoting. We calculate absolute maximum, absolute entries. It was 1, 0, 1, 1, 1, and 0. That is 1. And after changing the first column -1, -1, -1 to the 0, we will find this system. No, we want to calculate maximum again. We have minus 1, 1, 0, 1, 0, 1, 2, 1, 1, and 2. Maximum between 1, 0, 2, and minus 1 will be 2. It's this, these entries or this one. No problem. We can use the first one. We can use the second and the third. No problem. By using the first one, we change this one to the, excuse me. We change this one to the new pivoting. Okay, we do C24. That means substitute the second and fourth column together. We will find this one. 1, 1, 0, 0. This column is here. This column go to the fourth. This column is the same. And finally, this one, the first, fourth column, go to the second column. So again, we use this pivoting to change this one and this one to 0. We multiply the second row in minus 1 and add it to the third and fourth column. So we find 1, 1, 0, 0, first row, the same. 0, 2, 0, 1, the second row, the same. And minus 1 plus multiple minus 1 plus the second row and plus the third row. We want 0, we find 0, 0, 1, minus 2, and again 0, 0, minus 1, minus 2. Again, we calculate uh, maximum in this system. We have 1 minus 2 minus 1 minus 2. Maximum is here or is here, no problem. We change the second, the third, and fourth column. So this column is here. This column is here. The fourth column go to the third one, and third column will go to the last one. So again, we use these as a pivot and multiply this row by minus 1 and add it to the last row. We find first one again, second again, third again, and minus 1 multiple minus 1 plus this one change to 0, minus 1 multiple minus 1 plus 0, 0. 10 to 0, and finally minus 2. So you can see uh, we change the entries just multiple 2. Uh, at least we have all entries multiple 2, and it's not big to have overflow in our system. So we want to introduce some uh, special matrix. The first one is اکیداً قطر قالب سطری. Strictly row diagonality dominate matrix. اکیداً قطر قالب سطری. Strictly row diagonally dominated matrix. We want to know what's this matrix and what special uh, properties. We say if summation j from 1 to n, j except I, absolute aij, little, strictly little than absolute aii for I from 1 to n, it's اکیداً قطر قالب سطری. I told in Persian. I want to I don't want to say in English mode. اکیداً قطر قالب سطری. اکیداً غربی it's Arabic, قطر عربی, قالب عربی, سطر عربی, but you say in Saf. Uh, so you can find that. What this means? This means you can add all entry in every rows except in the original diagonal قطر اصلی قطر رئیسه you say in absolute mode summation must be little than the entry in the قطر رئیسه I will uh, tell an example. Also, we have اکیداً قطر قالب ستونی strictly gloom diagonally dominate matrix ستونی عمود you say it is summation from I from 1 to n I except j absolute aij little than absolute ajj j from 1 to n. If we change little than by little eq then it's we dropped akidan strictly will be dropped if we have equal here. Okay, let me to say some example. Minus 4 0 1 2. I wrote in the first in the original diagonal قطر رئیسی 8 minus 2 and 7. So all entries that I will wrote here must be little than 8. For example, in Java, here we can write 4 minus 2 and 0. All entries, this one, and this one must be little than 2. So if I wrote 1 here, that means we have to write 0 here and, for example, minus 0.5 here. All entries here must be little than 7, 3, 2, and 2. No, no, no. It's equal. 3 plus 2 will be 5, and plus 2 will be 7. It's not good as an example. I have to write, for example, 1 here, minus 1 here. It is اکیداً قطر قالب سطری. Minus 4 in absolute is bigger than 0, plus 1 plus 2 in absolute mode. 8 in absolute mode in the second row will be greater than 4 in absolute, plus minus 2 in absolute, plus 0. And minus 2 in absolute mode is bigger than 1, plus 0, plus 0.5 in absolute mode. And this last one. Also, if you consider this example, you find it's not اکیداً قطر قالب ستونی. It is اکیداً قطر قالب سطری. It is, but it's not strictly Coulomb diagonality dominate matrix, because minus 4 in absolute mode is not bigger than 4 plus 1 plus 3 in absolute mode in the first row. Coulomb. It's not correct. So this example is not strictly Coulomb diagonality dominate matrix. So we have some note here. In matrix اکیداً قطر قالب سطری or ستونی is non-singular. But if we drop اکیداً, it will be singular. Consider this one. A equal 1, 1, 1, 1. It's اکیداً قطر قالب سطری و ستونی. صف and قائم. The both this is, but the determinant of A will be 0. If we drop اکیداً, it must be singular and determinant A will be 0. To prove the non-singularity in اکیداً mode, if it was akid, let determinant A is equal 0. That means we want to use برهان خلف contradiction. If determinant equals 0, we know we have vector x non-zero, and ax will be 0. Matrix A multiple in vector x will be vector 0. Let the maximum xij for this vector in absolute mode occur in kth class. موقعیت کی، وضعیت کی. So taking the kth row of matrix of system AX, we have A from 2 n A kj xj equals 0. We stop A k k x k in the left hand and other turn to the right hand. That will be minus summation j from 1 to n A kj xj xj from k. We know xk is not 0. It's the maximum of entries in vector x. So we can divide it by xj. We have akk equal minus sigma summation j from 1 to n, j except k, akj, xj, x divided by xk. If we use absolute mode, we find akk little equal j summation j from 1 to n absolute akj xj divided by xk in absolute mode. This is little equal than 1 because xj is maximum of all xj. So we can write summation j from to n j except k absolute akj. It's contradiction because we assume the matrix is strictly row dominate matrix. So we have a corollary here. If A was اکیداً قطب سطری ستونی, then A transpose will be اکیداً قطب ستونی یا سطری. That means if A is row dominate, A transpose is clone dominate. If A is clone dominate, A transpose will be row dominate. Again, if A is اکیداً قطب ستونی is non-singular and we know it's absolute AI little equal than summation ji from to n AI1, that is little eq little just little strictly little than absolute A11. What's this? AI1 for all I between 1 to n. It's little from, excuse me, from I between 2 to n, all are absolute AI1 little equal than sigma I from 2 to n AI1, because it is here. And from this far's properties, we have little absolute A11. That means we have maximum entry in the first row, and we don't need to pivoting. Let me to explain more. Consider a system that is اکیدن قطب ستونی. We have here A11, A121, A31, and finally AN1. If we calculate absolute AI1 from I between 2 and from 2 to n, I mean these entries, it is little equal than sigma. Let me write k equal 2 to n absolute AK1, because AA1 is one of them. K from 2 to n is one of them. We have Far's hypothesis, that is summation k from 2 to n absolute AK1 is little than A11. So all I1 is little than absolute A11. That means it's the maximum in the first row. Also, I want you to prove after that we do the first Gauss elimination. We have A11, A12, A13, A1N, B1. It's not problem. Let me. This one will be 0, 0, and 0. We have here A22 in first phase, A23 in the first phase, A2N in the first phase, B2 in the first phase, A3 2 in the first phase, A3 3 in the first phase, A3N in the first phase, B3 in the first phase, and finally we have AN2 in the first phase, AN3 in the first phase, and ANN in the first phase, BN1. I want you to show A to 2 in the first mode phase in absolute mode is bigger of all A K2 in the first phase from car between 3 to N. That means it is a maximum between all of these. And again, for uh, third third phase of Gauss elimination and so on. Finally, I am saying that if you have a اکیدن قطب قالب ستونی ماتریکس اکیدن قطب قالب ستونی you doesn't need to you don't need to pivoting. This is a big conclusion, but you have to show that it's tamrin, it's practice. You have to calculate and send that to me. So uh, I wrote that here. I forgot. We have a matrix A. We do Gauss elimination. We find A11, A12, A1N, 000, and B in N minus 1 cross N minus 1. Again, we have matrix B اکیدن قطب قالب ستونی. So we dropped the first and second error in Gauss elimination. اشکالات اول و دوم روش حذفی گاوس در ماتریس اکیدن قطب قالب ستونی حذف میشه. We drop error first and second error in Gauss elimination in the uh, Clone dominate mode. Again, we want to introduce an special matrix. It is ماتریس معین مثبت positive definite matrix. A matrix say positive definite معین مثبت if it was symmetric متقارن and for all vector x non-zero x transpose ax that is a real number greater than zero. If a matrix has two properties, it is معین مثبت positive definite symmetric متقارن and x transpose x greater than zero. And if A is complex, their entries are complex number, it is for all x in C n non-zero, x star ax greater than 0. That is, x star is x conjugate transport transpose, that is x1 conjugate, x2 conjugate, and xn conjugate. Or we can write that x star ax, that is ax will be this summation sigma j as from 1 to n aij xj, and after that in x star, that is x summation I from 1 to n x j bar uh, will be greater than 0. We want to say some properties of positive defined matrix. Uh, but first of all, let me show some example. So we want to say some examples. Uh, 4 minus 2. Oh, it was must be symmetric. Minus 2, 3. This is a positive definite matrix because if you because you can see it's symmetric متقارن. Also, if we multiple x1 x2 in 4 minus 2 3 x1 x2, that is x1 x2, 4x1 minus 2 x2 minus 2x1 plus 3x2, and it is 4x1 over 2 minus 2x1 x2 multiple this one, that is, and minus 2x1 x2 plus 3x2 power 2. So we have minus 4x1 x2. Let me write 2x1 power 2 plus x power 2 plus 2x1 power 2 plus 2x2 power 2. I wrote 4x1 power 2 by 2x1 plus 2x1 power 2. And 3x2 power 2, I wrote x1 I wrote x2 power 2 plus 2 x power 2. So if you mm, notice that it is x2 x1, sorry, it's 2x1 minus x2. It's better to write that for 2x1 minus x2 power 2 plus 2x2. And if x1 and x2 will be non-zero, all of them, it's greater than 0. So it is the positive definite matrix. I want to show that. Let me to show what I wrote this matrix. I want to show that to you by writing some properties. First of all, eigenvalue of matrix positive definite will be positive. مقادیر ویژه از ماتریس معین مثبته. All eigenvalues of matrix positive definite will be positive. Why? Because if lambda will be a eigenvalue of A and X will be um, a vector eigenvalue, eigenvalue, eigenvector, excuse me, X will be eigenvector of A uh, from lambda, we have ax equal lambda x. A is eigenvalue of A, lambda is eigenvalue of A, and x is eigenvector of A. Mm, from lambda. We know x is non-zero, a vector that is non-zero. If we multiply this equation by x transpose from left hand, we have x transpose ax equal lambda x transpose x. Lambda is a scalar, so we can write that out of that, and x is a vector. We have x transpose ix equal lambda x transpose x. This is positive because A is positive definite matrix. Also, this is positive because x is a vector and it's non-zero vector. So divided these items and we find lambda is positive. And also it's not non-zero. So the second properties is consider the first property, that is all eigenvalue is positive. So determinant of matrix A will be non-zero. Also, we know determinant A is multiple lambda یک, lambda 1, lambda 2, lambda 3, lambda n. All of these eigenvalues are real because this is the symmetric matrix, and all of them is positive because it's positive definite. multiple these um, real number positive, we find a positive number. So determinant of matrix A will be positive, also will be non-zero. Uh, we can prove that uh, directly, not using in the first property. We use Borhan-Kolf contradiction. If determinant of A is equal 0, that means there exists a vector x non-zero, that is Ax equals 0. If we multiply this vector uh, mode equation, I mean multiple in x transpose from left, we have x transpose I Ax equal x transpose 0, that is 0. It's vector mode. It's vector mode. What is a scalar? Vector 0, 0. Just a number. So x transpose I will be 0. That is contradiction. So in positive definite matrix, we don't have determinant equals 0. Also, the third properties is all entries in the original diagonal is positive. قطر الرئيسية all entries is positive. Let's to show that let vector x is a vector, all entries is 0, just one of them is 1. It is kth place. So we know in this case x is non-zero because this entries is 0, is 1, and it's not 0. If we calculate x transpose Ax, that is summation I from 1 to n xi, summation j from 1 to n ai j xj, if we do that, this one, all entries is 0, j is changing, all of them is 0, except j equal a. So we have sigma I from 1 to n xi, ai j will be k, ai k. Again, all xj xi is 0 except uh, I equal k. So this is all of them will be 0 except a equal k, that is xj is 1, and it is akk. So it is greater than 0 for these vector non-zero vector, that is akk is greater than 0. Oh, we wrote that here. So all entries in the original diagonal is positive. If this one will be in first entries, that is A11 is positive. If this one is in the second positive, that means A22 is positive. And we do that in K plus place and show AKK is non-zero and greater than 0. 4. Again, properties of positive definite matrix, that is after doing the first phase of Gauss elimination. Again, matrix B is positive definite again. Consider A. We do that J Gauss elimination, J point, E point, Gauss elimination. We find these maths A11, A12, A1N, 000, and matrix B here. We can, it's n minus 1 multiple n minus 1. Now we say B is positive definite again. That is, you should show for all vector y non-zero vector I n minus 1 y transpose by will be greater than 0. You should show that it means B is positive definite again. Uh, all um, again properties of matrix positive definite is greater than entries in absolute mode of matrix A are in the uh, original uh, diagonal. بزرگترین درایه از نظر قدر مطلق از ماتریس A روی قطر اصلی در قرار داره. Greater than entry in absolute mode is on original diagonal. It's a practice for you to show that. Let me to say some uh, hint for you to prove this and this one uh, in future. I will show you some hint to prove this practice. I think you say that commas, ستة, I don't know. The six properties of positive definite matrices for all submatrix A will be positive definite again. That means if we use some index A1 greater than 1, little than, greater than or equal than 1, little than A2, little than A3, little than AK, that is little than equal n. This is some indexes. If we define AI1, AA2, AI1, I2, IK, we define in this mode. A I1 I1, A I1 I2, A I1 AK, A I2 I1, I2 I2, I2 IK, A IK A1, A AK A2, A AK AK. These entries of matrix A will be positive definite again. So if to show that, we want to show that, and after that, using these properties to prove this one and this one. Consider the first matrix is symmetric, so the submatrix will be symmetric again. That is necessary to show that for all vector y in arca non-zero, we want to show that y transpose ai1, I2, aik, y greater than 0. We show that, we want to show that this one. Let uh, vector x, that is all entries are 0, just in the a1 places it is y1. In a2 places it is y2. It is in ak places is yk. In other entries are zeros. Okay, x is non-zero vector, and if we calculate x transpose ax, it is summation I from 1 to n xi in multiple in summation j from 1 to n aijxj, that is summation I from 1 to n xi, summation j from 1 to k ai ij x ij. When these multiple uh, doing, all xj is 0 except xa1, xa2, xak. So these are all will be 0 except xa1, a2, ak. We change this notation by j from 1 to j, and we used aj by aij, this and this, axaj. We replace that uh, xaj by yj, and if we do this multiple, all of them is 0 except xl, il, I1, I2, ik. I wrote that al, L from Yek, A2, AK. We wrote them again by XJ, by YL, that is sigma L from 1 to J YL, sigma J from 1 to K A Y J, AIL, AIJ, that is Y transpose AI1, I2, IKY. So we know this is positive, that is mean this is positive. This corollary show that all determinant of all submatrix A, I1, I2, Ik will be greater than 0. And in the binary mode, if we consider 2 by 2, 2 cross 2, AIJ, that is AII, AIJ, AIJI, that is equal because it's symmetric, AJJ for I little than J, we have AIJ, AJJ minus AIJ power 2 greater than 0. If AIJ power 2 little equal M2, that means AIJ power 2 little than m power 2 if m is maximum a kk from k from 1 to n. That means m is maximum entries in the original diagonal. M is here, maximum entries. Aij power 2 little than m2, that is Aij little than m in power in absolute mode. What does mean? That it means the maximum entry in absolute mode will be occur in the original diagonal. بزرگترین درای ماتریس روی قطر اصلی قرار داره. Okay, so if you used this proof, you can do this practice and this practice. You have two practices here. If you use this proof, you can do them and send them to me. We return to solving system Ix equal b. We can use the matrix, inverse matrix. So for using a system Ax equal b, we uh, replace right hand, I mean vector b, by ei for I from 1 to n. That is, that means we can find A inverse. So we can uh, calculate them very good and بصرفه. I think it's Arabic word مقرون به صرفه. For example, we have a matrix here 1 minus 2 1 1 1 minus 1 3 minus 1 minus 1. Let me to check. uh, Mr. Ali, did you have any question? I sorry. Active your microphone now. It is good if you send me some messages, but you didn't send anything in WhatsApp because I couldn't see your messages in PowerPoint file. Mr. Ali Abdullah, when solving a question, where is this answer sent? You should send that to my WhatsApp, private my WhatsApp, and you should send by your name. Write that and picture and send that to me. I think, thank you. There is no problem. Let me to an example. We want to calculate A inverse. we have this matrix we want to use to find A inverse. First of all, we write this system x1 minus 2 x2 plus x3 x1 x2 x minus x3 3x1 minus x2 minus x3 all coefficients from A. In the right hand, we have 1, 0, 0. That is E1. That is 1, 0, 0. So we want to use Gauss elimination. We should use this entry, I mean 1, and change 1 and 3 to 0. That is R1, 2 minus 1, multiple this one in minus 1 and added to this one. Again, multiple this one by minus 3 and added to this one. We do R1, 2 minus 1, R1, 3 minus 3. We find this one. These are 0. But I note minus 1, minus 3 to looking that, to using that again. Again, we want to use this entry 3 and 5 to 0. That is operation R2 3 minus 5 divided by 3. We find minus 1 minus, so we find 1 minus 2 1 1, 3 minus 2 minus 1, and after that we find minus 2 divided by 3 equal minus 4 divided by 3. Minus 5 divided by 3, it's come from here. So we can calculate x3 from here. X3 will be 2. Put it here. Minus 2 to multiple 2 minus 4. Go to right hand. It will be 4 minus 1 will be 3 divided by 3, x2 equal 1. And if we put in first row, we find x1 1. 1 1 2 is solution of this system. Now we want to change right hand by E2. We change E1 by E2, 0 1 0. We do R1 2 minus 1, R1 3 minus 3. Multiple this one in minus 1 and add it to the second one. Multiple this one in minus 3 and add it in third one. It doesn't change. Again, we do R2 3 minus 5 divided by 3. Minus 5 divided by 3 multiple in the second and added in the fourth. We find this one. So we have to use this column by this column. We have 1 minus 2 1, 1 minus 2 1, 0. در عوض 1 minus 1 3 minus 2, substitute minus 1 by 1 minus 3 minus 5 divided by 3 minus 2 divided by 3. Substitute minus 4 divided by 3 by minus 5 divided by 3. If we do that, we will find x3 is 5 divided by 2. If we put that in the in the second equation, we find x2 equal 2, and finally x1 equal 3 divided by 2. 3 divided by 2, 2 and 5 divided by 2. It's for E2. For E3, we have 0, 0, 1. We do R1, 2 minus 1, R1, 3 minus 3. It doesn't change. We do R2, 3 minus 5 divided by 3. It doesn't change. So we solve this system. 0, 0, 1 comes from here. We find x3 equal minus 3 divided by 2, x2 minus 1, and x1 minus 1 divided by 2. So we have matrix A, 1 minus 2 minus 2, 1, 1, 1 minus 1, 3 minus 1 minus 1 in x1, x2, x3, x prime 1, x prime 2, x prime t, x second 1, x second 2, x second 3 equal 1, 0, 0 for x1, x2, x3, 0, 1, 0 for x prime, 0, 0, 1 for x second. If we solve this system, we find x1 1, 1, 2, 3 divided by 2, 2, and 5 divided by 2. 1, 1, 2 for x, 3 divided by 2, 2, 5 divided by 2 for x prime, and minus 1 divided by 2, minus 1, minus 3 divided by 2 for x second. That is A inverse. So by using Gauss elimination and doing a good operation from Gauss elimination, we can find A inverse. It must be useful to our calculating. We want to calculate all operation. Ax equal B, it's matrix. I wrote that in chapter mode. B, we do that Ri1, Mi1, I from 2 to n to find B1. And again, we do R2I, Mi2 from I equal 3 to n to find B2 and go to find the finally. Here we have n minus 1 multiple or divided, and also n minus 1 plus or minus. Here we have n minus 2, and finally to find 1. That is n multiple n minus 1 divided by 2 multiple and divided plus and minus. That is order n2. It's very good to use to find A inverse, not using linear algebra method. General operation will be multiple, also multiple and divided, jam, plus and minus. Gauss elimination, we find that it is n power 3 divided by 3 multiple, n power 3 divided by 3 summation. Solving upper triangular system, we find n power 2 divided by 2 multiple, n power 2 divided by 2 summation. Uh, Changing right hand by transformation, by transformation we find n power 2 divided by 2, n power 2 divided by 2. If we calculate them, it's n power 3 by 3, and it's n power 3 by 3. It's ordered n3 for calculating A inverse. We find the second part, that is decomposition LU for matrix A. Let me to stop here. My lecture will be here to next week. These these files these files are in our website, in university site. I hope we find a translator to translate them to and send that to you to find your Arabic language and well down to read and understand it. Is there any question? Thank you, everyone. Have a nice day and nice night. مع السلام. خدا نگهدار.